Hi everyone, my name is Yong, and I'm very excited to talk about how automatic differentiation works in Slang in this next part of the course. So far, we've talked about the core concepts of neural graphics and how you can incorporate an MLP into your shader. You may be curious how Autodiff works in the MLP training code you've just seen, and that's what I will cover next. By end of this section, you should feel comfortable writing your own differentiable shader with Slang. Specifically, I'm going to talk about two modes of Autodiff that Slang supports. That is forward and backward differentiation. I will talk about how Autodiff works with custom types in Slang and how you can define custom derivatives. Finally, we will cover how buffer access is handled by Autodiff so you can propagate gradients back into your global memory buffers that host neural network weights, image pixels, or vertex positions. Without further ado, let's get started. To understand Autodiff, let's start with a very simple function that computes the sum of squares from x and y. And we can also write an entire entry point function that calls into square and print the result. Note that although Slang is often used as shading language, it also has the toolset to interpret and run code like this completely on the CPU. If you download the latest Slang release package, you will find a tool called Slang-I, and you can use it to execute code on the left. And if you do that, you will see the result printed from the console. With the function defined, we can simply mark the function with the differentiable attribute to tell the compiler that we need to propagate gradients through this function. This allows the compiler to automatically generate both the forward mode and backward mode gradient propagation functions from the square function. You may be wondering, what are these gradient propagation functions? And let's get into that. First, let's talk about forward gradient propagation. In simplest word, forward differentiation is the process of finding the derivative of a function, exactly as what we learned at high school. In this case, the derivative of the square function is 2x plus 2y. In Slang, we generalize this a bit further, so the forward derivative function will take parameter x, y, and additionally the gradient values dx and dy, and returns 2x dx plus 2y dy. You may wonder, what exactly are dx and dy here? Well, dx and dy matters if x and y are not just constants, but computed from some other terms themselves. Assume you have computed the values of x from an upstream value theta and values of y from an upstream value gamma, and you compute s by calling square with x and y. Now, let's say you already know the gradient of x with regard to theta and the gradient of y with regard to gamma. This is what we call dx and dy. And now you want to find out the gradient of s with regard to the upstream values theta and gamma. That is partial s partial theta plus partial s partial gamma. Or in a more verbose form, that is partial x times partial x partial theta plus partial s partial y times partial y partial gamma. Back to our square function, this can be noted as 2x dx plus 2y dy in short. That's the full mathematical definition of forward differentiation. This is called forward differentiation because you are propagating the gradients of x through the square function to get a gradient of s. You can compute forward gradient propagation very easily with Slang. Let's say we want to evaluate the gradients at x equals to 3 and y equals to 4. We will call the built-in diffPair function to construct a pair that holds both the original or the primal value of x, that is 3, and we also set dx and dy to 1. Next, we are going to use the forward diff operator in Slang to invoke the forward gradient function of the square function. You can view the forward diff as a higher order function that takes square as input and returns the forward gradient propagation function for square as output. The forward gradient function can then be called with the pairs we just constructed, allowing both the primal and the gradient value to flow through the function. If we run this code, we will get 14 because when we plug in x equals to 3, y equals to 4, and dx dy equals to 1 here, we will get 14. As a small extension, let's consider a slightly different problem. What if we want to know the gradient of x, that is partial s partial x, and exclude the gradients for y or gamma? Well, we know the forward gradient function computes partial s partial x times partial x partial theta plus partial s plus partial y times partial y partial gamma. If we pass in 0 for partial y partial gamma and pass 1 for partial x partial theta, the result would just be what we want, that is partial s partial x. And this is how you do it in Slang code. And when you run it, you will get 6 because partial s partial x is 2 times x. So this is how forward mode auto differentiation works. Similarly, how do we find out partial s partial y? We will just flip the gradient values we pass in to set partial x partial theta to 0 and partial y partial gamma to 1. This way we will be computing 2 times y, and that is 8. As you can see, with forward differentiation, if we want to find out the gradient with regard to each single input parameter, instead of the aggregate of all the input parameters, we need to call the forward diff function once for each single input parameter. The square function has 2 inputs, so we need 2 separate calls to find the individual gradients. In machine learning, a neural network can have thousands to millions of parameters, and it would be impractical to call forward diff a million times to find out all those individual gradients. So what we can do, for this, we need a second form of differentiation that's called backward differentiation. The main advantage of backward differentiation is that it can be used to find the gradients for all the individual inputs in a single call. To understand that, let's take a look at the mathematical definition of backward differentiation first. This time, assume we have computed the term s by calling square, and then we use s to compute some downstream term l. Now, if we already know the gradient of l with regard to s, that is partial l partial s, the task is to find the gradient of l with regard to x and y, or more verbosely, find out partial l partial s times partial s partial x and partial l partial s times partial s partial y. As you can see, this is propagating the gradients from the output of the square function s to the input of the function x and y, and so this is called backward propagation. So this is how we do it in Slang code. First of all, we are going to construct diffpairs as usual. In addition, we are going to specify that a partial l partial s is 1. Next, we call the backward diff operator to this function will take square as input and give us the backward derivative function for square as output. And then we call that function with the pairs we constructed and with the dl d square value. The backward prop function is going to read the original or the primal values from a pair and write the propagated gradients into the gradient part of the pair. And then we can access those gradients with x.d and y.d in this print statement. Finally, we can run this code with slang I, and it will return the gradients for both x and y in one go. And that is how forward and backward derivatives works. In short, forward derivative computes the gradients of output with regard to all the input parameters. Forward derivative functions runs faster than backward derivative functions, but you will need to call it once for each input. It is most useful when the number of input you want to compute gradient for is small, such as computing the normal from an SDF or texture coordinate gradients. In contrast, backward derivative functions compute the gradient of output with regard to every input parameter in one go. This means that the function is more complicated, but you only need to call it once. It is most useful when there are a large number of inputs that you want to compute gradients for, such as when in a neural network code you want to figure out the gradients for each weight. With the basics covered, let's take a look at how Autodiff works with other existing language features. At this point, you may be wondering, how does this work with my own struct types? For example, what if instead of taking x and y as floats, as floating point inputs, what happens if we modify this square function to take a custom type called point here? For that, Slang introduces the concept of the differentiable type and non-differentiable types. Consider this slightly different function called run. This function contains one input integer parameter up and two floating point parameters. It doesn't make a lot of sense to ask the compiler to compute the gradients of up, since an integer value is intrinsically discontinuous and can't have gradients. So the Slang compiler needs a way to tell apart differentiable terms from non-differentiable terms. If you are in Visual Studio Code with the Slang extension installed, you can get IntelliSense for your function signatures. Let's say you put a caret here and hit Ctrl plus space to pop up that signature help. Here is what you will see. The Slang language server is telling us that the forward gradient function of run will take three parameters. Notice the difference between the op parameter and a and b parameters. The type for the op parameter is unchanged between the original function and the forward gradient function. This is because Slang is treating int as a non-differentiable type, which can have gradients. In contrast, the a and b parameters change from being a float to a differential pair of float, allowing it to carry both the primal and the gradient values into the propagation function. This is because float type is a differentiable type that can carry gradients. So how does Slang make the distinction between differentiable and non-differentiable types? This is achieved through a built-in interface called iDifferentiable, which defines a set of requirements that the type has to meet to be considered differentiable. These requirements define how to represent the zero gradients and how to do multiply or add on the gradients. By default, floating point scalars, vectors, or matrices are considered differentiable, and an array of t is also differentiable if t is differentiable. If we go back to our previous example to pass the custom point type to square, the signature of the forward diff function will look like this. As you can see, the compiler is treating point as a non-differentiable type by default, and the gradient function is accepting p as is without taking in a pair of primal and gradient values. To allow gradients to propagate through the struct, you can simply add a column iDifferentiable clause to the point type. This will cause the compiler to treat point as a differentiable type. With this, the signature of the forward gradient function will now take in a pair. And that's how custom types are going to work. Next, let's talk about custom derivatives. Consider the square function. Now let's say for some reason you don't want to use the compiler-generated gradient function, and you want to provide your own implementation of the forward or backward gradient propagation functions because you know a better way of computing it. You can do that by implementing the gradient function and use the forward derivative of attribute to associate it with the original square function. With this, the compiler will use the provided implementation instead of the automatically generated one. Similarly, you can use the backward derivative of attribute to provide a custom backward propagation function. You may wonder, why do I need to care about custom derivative functions? As Benedict and Chris has shown you earlier, Custom derivatives are often used to write backpropagated gradients into buffers. Consider this variant of the square function. Instead of taking in a value of y, it now takes an index into a buffer where the value of y is fetched from. The question is, how would you backpropagate gradients into the buffer? After all, the y_idx parameter is now an int, which is non-differentiable. So the signature of the square's backward gradient function now takes the index as is, and there's no additional differentiable pairs to receive the gradients of y from the call side. The pattern to solve this problem is in 2 steps. First, we wrap that buffer access into its own function called getY and modify our square function to call getY instead. Next, we provide a custom gradient function for getY, which writes the gradient propagated to the function into a separate global buffer holding the gradients. With this setup, the gradients for y will propagate through the call to getY, and the compiler will invoke the getY_bwd function, passing the gradients propagated so far as the dout parameter through the call. The custom gradient can then simply write that value into a buffer that receives the gradients. Another use of the custom derivative is to help debugging the intermediate gradient values. Let's say we wrote the square function by computing the squares in separate steps. And now we want to figure out during a debugging session the gradients of L with regard to y2. But since the backward gradient propagation function is compiler generated, there is no way for us to modify that code to inject a printf. So what do? The answer is we can introduce a trivial function called debuggrad that simply returns the parameter as is. And then we can write a custom backward gradient function for debuggrad that prints dout and propagate dout through the differential pair for x. With that helper function, you can then wrap any term in a differentiable function with debuggrad, which will cause the backward gradient function to print out the gradient for that term while keeping the primal computation identical. This pattern can be very useful in debugging gradient values when writing differentiable code. You can think about backward gradients as a way to register a callback to intercept the gradients propagated so far, so you can do whatever you want with it, either print it out or write it into a buffer. And that concludes this section. To wrap up, we have covered the definition of forward and backward propagation functions and how to initiate forward and backward mode differentiation in Slang. We discussed the notion of differentiable and non-differentiable types and how to introduce custom differentiable types to the compiler. Finally, we talked about custom derivative functions and how they can be used to propagate gradients into buffers or debugging gradient values. The full Autodiff system is documented in Slang's user guide, and I recommend reading the full chapter on Autodiff if you are interested in understanding Slang's Autodiff in greater detail.